So what we talked about the other night was basically just a little introduction into semiconductors. Right? We talked about, and this is the newest PowerPoint. This chart is a lot prettier than the other one we looked at the other night. That shows you the rating of conductors. Of course, the best conductor is silver, followed by copper, followed by gold, followed by aluminum, and then we get on down. This goes all the way down into the mercury. So these are all metals. The one chart we had up the other night showed like air, showed some insulators too. This is all just strictly conductors. Some of these we actually use inside heaters. So we don't want, if I'm going to heat with a piece of wire, we want it to act like a resistor, right? So we'll use like nickel or tungsten. Tungsten is used a lot as a heater element because it has a bigger R, and you get heat when you run what? The filament bulb, the filaments on incandescent lights are tungsten. So even though they're conductors, they're considered to be conductors, they still have a pretty good deal of resistance, so they get pretty hot when you heat them up, right? Huh? So then we looked at the atomic structure. We talked about what made. We talked about the valence shell, which is the valence shell? The outer shell has a minimum of, maximum of 8 if everything's balanced, right? And anything 1 to 3 makes good conductors. 5, 6, 7, and 8 makes good insulators, and 4 are what? Semiconductors. They're right in the center. So that's how they got their name, really. Even though we dope them to make them conductive, so we don't make them pure anymore. So the valence shell, we talked about the way we looked at the conductors, and so basically all your conductors fall into the top part of row 11. So there's copper, silver, gold, and aluminum. And then your semiconductors are over here, and aluminum is over here by itself. So aluminum has got 3 conductors out there, got 3 out there in the valence shell. So it's right on the edge of not being a conductor, right? You understand? Even though it's probably the second most widely used conductor out there. And these are your semiconductors down the line right here, line 14: carbon, silicon, germanium, tin, lead, and this is labeled wrong. It actually starts with an F. These are the two. These are readily available. These are most widely used, and also carbon is in the form of powder, so it's real hard to work with. So these are the 2 most powerful used right here, silicon and germanium. Originally, when they first started with semiconductors, they used germanium. And then over time, we have migrated to silicon. So silicon is by far the most widely used semiconductor currently because of its temperature characteristics. It's better at higher temp, operates better at higher temperature. This was a little chart, and this is good too because this shows you the bands. And then it shows you the very last bottom one is the valence shell. And you see copper has 1, silver has 1, this has 1, and then aluminum, and I covered it up, has 3. So this is why aluminum has more resistance. So what do we use to compensate for the resistance when we use aluminum? Originally, aluminum's got problems. Aluminum has a big coefficient of expansion and contraction, so that means it really changes shape a lot when you heat it up and cool it down. So aluminum is hard to keep tight. I mean, it'll work itself loose. Another problem we have is that it oxidizes really fast. So aluminum oxide is an insulator. So they started to save money. They started wiring house trailers with aluminum. Another thing we have problems with is, y'all ever heard of dissimilar metals? Mixed dissimilar metals. When you put 2 dissimilar metals together, it sets up what we call electrolysis, which makes them corrode a lot faster, and they'll sit there and eat themselves up. Copper and aluminum are dissimilar metals. So we cannot directly mix copper and aluminum. So they were buying these house trailers, and they started wiring them, and these electricians didn't know that, and they were buying copper. They were buying copper plugs and putting aluminum wire around it, and they were burning up house trailers left and right. So no, but they do have a paste. If you're going to deal with aluminum, and my son's got aluminum in his house. His house is pretty old, so his house is aluminum wire, and he refused. He won't buy a copper plug since I told him that. Even though you can buy a paste that you put around the aluminum to keep it from oxidizing. You can't keep it from expanding and contracting, but you can keep it from oxidizing and messing up your copper wire. So up there, when it comes from your house, so the downdrop from the house is probably aluminum. You took all that tape off of that splice up there, you see it's got it looks like grease, looks just like grease all over there to keep the what? Keep the oxidation away from the aluminum and the copper. But what is the advantage of using aluminum as a conductor? Yeah, cost. I mean, we're talking a big cost. So what we do is we compensate for its resistance in transmission lines by using an extreme high voltage, right? So, because when we're delivering power, and power, you wasn't in here the night. I don't know if Randy, if you had already left or not, but what's the basic formula for power? That's a formula y'all should know. What's the basic formula? Yeah. So power is equal to, no, I did it then. I put my arm down on my thing, so I don't know what I did. I don't have a blank on here. Yeah, I need to keep this thing out of the way. So what did I do? Turned it off. I know it isn't. The screen is lit up. It's just blank, and it don't have a blank. It don't have a blank on the button. There it is. I hit user. Yeah, so power, electrical power is equal to voltage times current. Well, if we rearrange the formula inside for I is equal to P over V. So what we're trying to transmit is power, right? You understand? So the higher we make the voltage that we transmit it at, what happens to current? Yeah, it goes down. So what we do is, this is what these high tension lines are doing. They step the voltage up extremely high for transmission, and then they step it down for safety. And that's why they use aluminum. So your what we call our high tension lines, or our higher voltage lines, use aluminum. And some of your lower voltage lines still use aluminum, but when they start getting down around your house, that's going to be copper, right? There's your semiconductors. We looked at, that wasn't on the other slide. How bonds, this is the video. I posted a video up on Blackboard for y'all to see it. We got two main ways of bonding. What we have is an ionic bond, and then we have a covalent bond, right? Y'all understand that? Silicon material, we know most common is germanium and silicon. These are germanium and silicon. Of course, silicon, by the way, is the most widely used now. And then germanium is a little more susceptible to temperature changes. We look at covalent bonding. This is what silicon does. Pure silicon will bond so what we're doing is looking right in here. So this is what they're trying to do. So if I count these electrons, 2, 3, 4, 5, 6, 7, 8, and that's what a covalent bond does. It tries to get how many out there? 8. That's what covalent bonds do. So ionic bonds, you get a real strong atom, and it literally jerks electrons out of the atom, out of the other device, right? You understand? Of the other element. Of course, there's no such thing as pure semiconductors. We call this intrinsic semiconductors, but we can't make them perfectly pure. So we got some impurities there. We have current flow through this thing, but we have two types of current flow that we understand now. What's the two types of current flow we have? Yeah, we have electron flow, and we have what we call hole flow. And we need to understand those two. And I think we got a thing here that kind of shows you what's going on. I like this. So what happens when we got a conductor? It don't make any difference if it's a conductor or anything. When I come over here and put a potential on this thing, let's say a big negative and a positive over on this side, then that negative is going to bump an electron out of into the conduction band, right? And it's going to move. Well, as soon as it moves, it's going to create the absence of an electron out there, and we call that a hole. Now, as soon as that happens, it's got another electron's going to push in there, right? You understand, right? And it's going to start bumping and bumping. So what we have is that in a conductor, we have two types of current flow. We have two things flowing in the conductor, right? We have what? We have electrons flowing from negative to positive, and we have holes flowing from what? Positive to negative. That makes sense. There's actually two types of current flowing in a conductor. Two things. It's not current. Current is electrons in the conductor. But we do have two things flowing.
So, when you stress quartz, which is silicon, you're able to get electric charge out of this.
No.
No?
You get current flow. It's a semiconductor. It's not a photovoltaic cell. We can expose it to certain things and do get a voltage out. So silicon works on that principle. I mean, not so, a solar cell works on that principle, right? But it's a semiconductor, but it's absorbing the energy of light to produce electrons. Now this is just current flow. So in current flow in a semiconductor basically acts like current flow in a resistor. And we have inside a semiconductor, we have hole flow with that hasn't been doped, and we have hole flow and we have electron. You need to move up one, check. Or two, whichever one you want. The problem with this is that if we come up here and heat it up and it's not in there, what happens to semiconductors? It operates opposite from conductors. Metals, when you heat them up, their resistance goes up. Semiconductors, when we heat them, the resistance goes down. Because it's just like most things. Metals are a little strange, but most things, when you heat them up, the atoms become more active. And they become more active, more electrons can move up into that conduction band where they can be moved. In fact, I think y'all told that. We have a device called a thermistor, which is a semiconductor that we use to measure temperature. And that's exactly the feature it's using. Okay, then we went into what? Then we went into what we call a p-n junction. So what we do is we deliberately, we call it doping, or they call it doping. I had nothing to do with these names. So what we do is we introduce a pentavalent, which would be it's got 5 electrons in the valence shell, and then we force that into the crystal, and then it'll bond. And what we end up with is an electron that just moves around. Because now we have 9, and how many do we need? We need 8. So it's still there, and we call it an N material, but it literally has no charge, right? Because the protons in the crystal still does what? Matches the electron. It's just that now we've got an electron in the conduction band. Oh, no, this is the wrong slide. So, sorry. This is the last one we looked at. So we're looking at Where was it at? Was it in the first one? We had one strictly on doping. Oh yeah, so this is what we're talking about. So if we heat it up, then we get more free electrons and the resistance actually goes down. Undoubtedly, I've lost the PowerPoint. So what we do when we dope a semiconductor is we introduce impurities into the crystal. I'm trying to see if it's up on Blackboard. You don't see one labeled doping, do you? Could be something that wasn't recorded. This is when we bond an N material with a P material. This is formed what we call a P-N junction. Now, as soon as we form the junction, as soon as they're pressed together or formed together, then what happens is these electrons over here in the N material try to migrate into the holes in the P material, right? You understand? And what happens is we end up with a section in here that is referred to as the depletion region. Because in that depletion region, there's nothing in the conduction band. Y'all understand that? Now what this causes to happen though, is it causes ions to form on both sides of the P material and the N material. So what we end up with is we end up with a little tiny high resistance. In fact, it actually looks like this. Voltage source. We can't get any work out of it because it's a high resistance voltage source. And what we talked about the other day, a lot of people don't understand how much current flow you get out of the source is determined by the internal resistance of the source. That's why we don't kill people with static electricity, because your body is a high resistance voltage source, right? You understand? So as soon as you arc, that voltage drops down to what? 0 instantly. So we can't get any work out of this little old tiny battery, but it's there, and we've got to overcome this thing before it conducts. We call this the forward. We call this the this in data sheets. This is going to be called VF. This is the forward voltage across the diode that can be measured with an extremely, can't be measured with an ohm meter, because even though an ohm meter has a extremely high resistance, it's still not high enough to get a voltage off there. We can't measure it with a voltmeter. So what we do is we measure it with an ohm meter, because the ohm meter turns into a voltage source. Does that make sense? And so we got a voltage. So I could take a 9-volt battery and put a resistor in series, and I could hook this up, and then we would measure it's approximately 7/10 of a volt for silicon. Now notice I'm saying approximately, because it has an R and it varies with current. So this is what we use. Some books teach 700 millivolts, so most people say 0.7 volts. We don't say 700 millivolts for this for some reason. This is for what? Silicon, and approximately 0.3 of a volt for germanium. And if you look it up on data sheets, it's going to be labeled VF, forward voltage drop. So if you got a good old ohm meter, if you put it on about the R times 100 scale, what's going to happen is when you put and this is what becomes very interesting. And let's typically show it. So barrier potential. Everybody understand what we call the barrier potential? Everybody okay? All right. Now what's going to happen, what becomes very, very neat is when we put a voltage across this P-N junction. This is where we left off the other day. We call it biasing. Bias is a DC voltage, so you'll need to write this down, that we apply to a semiconductor to establish or set its operating parameters. So a P-N junction, we have two types of bias. We have what we call forward bias. This is a condition that permits current flow through the junction. We have what we call reverse bias. This is a condition that prevents current flow through the junction. Y'all understand that? So we're going to be using that term all term long. When we get into transistors, we're going to say, okay, to make it operate, we have to forward bias it. If we don't operate, we're going to have to reverse bias it. And then we'll figure out what voltage levels and what polarities are required to forward bias the thing to make it work, and to reverse bias it and make it, we can't say work, it's doing its job. So we reverse bias it to prevent it from conducting current, and we forward bias it to do what? Make it conduct current. Everybody okay? So what is bias? These are always DC voltages that we apply to a semiconductor to set its operating parameters, how it works. And transistors are really, really neat. So forward bias permits current flow, acts like a closed switch. A diode would never be a closed switch. A closed switch, basically, if it's a good closed switch, that sucker's going to drop 0 volts all the time. This guy here is going to drop at least 0.7 of a volt. And that 0.7 of a volt is going to vary with current. So that means if I go up toward the maximum current, it's going to go up. If I go down below that, it'll probably cut off. That makes sense? A negative terminal DC bias is connected to the N region. This pushes the electron toward the junction. The positive terminal of the DC supply is connected toward the P region. This attracts the electrons in the P region away from the junction. So this is forward bias. Let me exit this and get rid of this. This is left over probably from last class. Okay. So one thing, number one, when we forward bias a diode, it's going to act like a closed switch. If you put a closed switch across two power supplies, you're going to end up with short circuit, right? You understand? So when we forward bias this thing, we're going to make sure we have some type of resistor in there to limit the current. Y'all understand that? We cannot put a switch between the common and the neutral on our house. Y'all understand that, right? So when we forward bias the diode, we're going to have a resistor in there to limit the current. Everybody okay? So what we're going to do is we're going to forward bias it. So I've got a DC supply out here, and we're putting the negative's got to point toward the watt, N, and the P has the point toward, the positive has the point toward the P. Now what happens is this what's going to happen? So what's going to happen is this negative is going to come over here, and it's applying a push in this direction. Inside the N material, we got a lot of free electrons up in the conduction band. So what's those guys going to do? It's going to start pushing that thing. As soon as it starts pushing, what's going to happen to the size of the depletion region? It's going to start doing what? Going down, right? As soon as we get up to about 0.7 of a volt, we've collapsed the depletion region. Now these electrons are going to move right there. Now as soon as those electrons hit right there, what are they going to see? Well, they're going to see that big old positive right there of the battery, right? They're going to start dropping into holes, right? You'll understand that. These guys here, this is going to push the holes in this direction. This is going to push the electrons in that direction. And they're going to just start doing what in the center? They're just going to start combining, right? So what do we have over here? We have primarily hole flow over here. Over here we have primarily what? Electron flow. Out here we have hole flow and electrons out here in our conductors inside the semiconductor, hole flow in the P, electron flow in the N. And what they're doing is just doing what as fast as we push them in here and push them that way, they're combining at the junction. So what we're doing is we're pushing them toward the center, and as soon as we get up to what? About 7/10 of a volt, then the thing's going to start conducting. So that means if I come over here and I measure across my silicon, we're going to measure VF. For silicon, it's going to be around 7/10 of a volt. For germanium, it'll be around what? 3. All the rest of the volts is going to be dropped across the resistor. So until I get up to VF, the only current that we have flowing through the semiconductor is what we call, the diode is what we call leakage current. So there is going to be current. We'll try to measure that, but it's going to be in the range, and it's in the data sheets. We're looking at nanoamps. So for all practical purposes, nanoamps is what? Basically nothing, right? You understand that? We get up into the forward bias of this, it's going to depend on the diode, what it's designed around. But it is going to drop a voltage, and it is going to have an R, which means it could get hot, right? You understand? So these guys are going to be rated at a current. If you get above the current, it's going to be an maximum current. If you get above that, it could do what? It could burn it up. So if I need to go to a higher current, what am I going to have to do with my diode? I'm going to have to make it bigger, right? So what happens, so if everybody's okay on 7, so if I was biasing this with 10 volts, then what I'd have is I'd have 7/10 of a volt across the diode, and then I would have 9.3 volt drop across the resistor. And we'll talk about measuring this relative to common. People think to forward bias a diode, you have to have 7/10 silicon diode, about 7/10. Your cathode has to be, we didn't talk about cathode. The N material, what do we call that? And the P material, we call that the what? So to forward bias a diode, you need to have the silicon diode, you need to have the cathode 7/10 of a volt less positive. It can be more negative or less positive, right? You understand? A lot of people, when we'll say to forward bias a diode, the P has to be a positive and the N has to be negative, that's totally false. You'll probably never see that. Because if I was to come over here and make this my common, right? Make the negative my common on my meter, and I measured right here, it was going to measure 0. Is that negative or positive? Neither one. If I come over here and measure right there, it's going to measure plus 7/10. So the cathode's not negative, it's sitting at 0 potential, but it's negative in respect to the what? To the anode. Everybody understand that? So to forward bias this thing, we got to make the P material less negative than the cathode. Does that make sense? Or we got to make the N material less positive than the anode. And so a lot of people think if you see on a test where it says the P has to be positive and the N has to be negative, you better mark that false. Because odds are we're going to have a resistor in there. And that resistor is either going to make both sides positive or it's going to make both sides negative. Y'all understand? So if I came over here and used this as my common, if I came over and measured this, it's going to measure 9.3, right? You understand? Right? I'm sorry. This would measure a minus 10. This would measure a minus 9.3. So this is a minus 10. This is a minus 9.3 because it's relative to where you make your measurements at, right? Because this resistor is dropping how many volts? 10 volts. So here we're making this our common, right? You understand? So I go here. This is going to measure. I need to think about that. Yeah, and over here we would have 0, right? So this would measure minus 9.3. This would measure minus 10 because we're making the positive our common. Once electrons enter the P region and combine with the holes, they are valence electrons and move from hole to hole until they reach the positive source. The P material, the holes are produced in the opposite direction as electrons. Therefore, the majority carriers are producing current in the junction. So in the N material, what's the majority carries in the N material? Electrons. And what's the majority carries in the P material? Holes. And this is what they're showing. That's a good picture. This is not in your book. This came out of a book by Floyd. And they show the barrier potential. But
So in a light emitting diode.
we're not talking about light emitting diodes. We're talking about diodes. We got lectures on light emitting diodes. What happens on a light emitting diode when they combine at the junction, they release photons. And the amount of energy determines the amount of photons. A PN junction, silicon releases so few photons, and they're at a wavelength you couldn't see. So we cover those up. Everybody okay on the barrier potential? The depletion region opposes the forward bias, the negative ions near the junction. And this is just a bunch of bull. We already talked about that. So this is what we're dealing with, right? You understand that? And this is why you can't get any work out of the barrier potential, because we have these resistors in the end. Okay, y'all understand that? Okay, so what's going to happen? Conduction occurs approximately 7/10 of a volt for what? Silicon. And that's what we'll use. I think the book teaches 7/10, but a lot of books you get, they talk about 6/10. Who's right? Both of them. This is just an approximation that we use that works real well for calculations. The actual voltage drop across the junction varies. The more current you put through it, it goes up. The less current you put through it, it goes down. Once you get below the VF of that diode, which is probably around 5/10. So around 5/10, it starts conducting a little bit. Then it'll take off, and we'll show y'all the actual curve here in a minute. But if you're not into engineering and that kind of stuff, 7/10 will work out great in our math. And this is what they're showing you here. So let's see if we get the reverse bias. Reverse bias prevents current flow, acts like an open. It is not an open, it acts like an open. And there is current flow through it because there is a path. If you have a path between point A and point B, then current is going to flow. It's just that the current will be so small that we can't measure it. We're going to measure it. But to measure it, what we're going to do is we're going to reverse bias the thing, and we're going to put like a 10 gig ohm resistor in series with it. So we can measure that voltage drop, and then we can measure nanoamps, right? You understand, because we'll have such a big voltage drop. To prevent current flow, it acts like an open. The negative terminal is connected toward the P region. The positive terminal is connected toward the N region. And what we're going to do is we're going to pull the electrons and the holes away from the junction. So what's going to happen is we're going to increase the barrier. Y'all understand that? And it's going to be equal. Now the barrier will be equal to the applied voltage. Now you have to understand, when you put enough voltage across everything, you're going to have current flow. So this guy is going to have a rating called the breakover voltage. We never want to exceed that, because that means you're going to force current through the reverse bias diode, it's dropping a lot of voltage. It's going to produce a lot of heat real fast. And what's it going to do? It's going to burn up. So we need to make sure we stay below the breakover voltage for the diode that we've selected. So that's one of the parameters on the diode. It's not only how much current it allows, forward current it allows, the maximum current it allows, it's also over what voltage it will probably break over at if you exceed it. Reverse bias condition, the depletion region gets what? Wider. Because that's what we're doing. If we have a depletion region and now we're sucking electrons this way and we're sucking holes that way, right, you understand the depletion region just gets wider. But there is a path. There is current flow through there. So we can't say there's no current, but the current flow is going to be determined by temperature. And that's what we'll do. We'll get a heat gun and we'll reverse bias it. We'll put that 10 mega ohm resistor. So when we break it over, we're going to break it over on purpose, but we're protecting it with a big old resistor, right? You understand, to keep it from burning up. And we'll heat the diode up and we'll see the voltage drop across that 10 gig ohm resistor go up, and we'll cool it and we'll see it what? See it go down. But we call that leakage current. So there is current flow through it. If I open a switch, there's no current flow through it. If I close a switch, if it's good, there's no voltage drop across it. Everybody understand that? This is not a switch. It's a semiconductor, a doped semiconductor. So it will never drop 0 volts when they are forward biased, and it will have leakage current when you do what? When you reverse bias. Remember, DC resistance of a capacitor is extremely, very, very large. So it actually acts like a capacitor. In fact, we have some of these guys, we can actually change the reverse bias on it and change the capacitance, which is pretty neat. If you hadn't had AC, don't worry about it. We'll talk a little bit about AC in a minute. So this is what happened when we reverse bias that guy. The depletion region just gets what? So if I came over here, and we don't need a resistor, by the way, because but if we had the original circuit that we had, and then we would have a resistor over here. And then I would come over here. What would we measure across the resistor? If this right here was 10 volts. Yeah, I would measure just about 0 volts. In fact, that's what we measure. Why don't we measure voltage? Well, V is equal to what? I times R. If V is equal to I times R, we have 0 I. And no matter what size R is, we won't see it. Unless it's a 10 gig ohm resistor. But a 10 gig ohm resistors, you're not going to see very many of those because that's almost an open, right? You understand that? What should we measure across the diode? Very important to know, guys. Should measure the source voltage, right? Because this guy here is dropping. If this guy's dropping no voltage, it's acting like a piece of wire. This guy is dropping no voltage, so it is a piece of wire. So that's why you measure the applied voltage across an open in a series circuit, not in a parallel circuit, in a series circuit. So the entire voltage will be across the diode, and then if we forward bias it, we'll get about 7/10 across the diode and about whatever minus that is. Now the 7/10, we'll look at that in a minute. We'll look at different approximations. Reverse bias of the diode causes the current to come. It don't say what. It says practically 0, right? However, there is a small amount of current that is produced by minority characters in the region. We call this leakage current. This current is usually in micro or nanoamps, and it's IR in your data sheets. This reverse current depends on the junction's temperature, not on the amount of reverse voltage. Everybody understand that? And this is showing you what's going on. Nice picture. And this is what we do. occurs when enough reverse bias voltage is applied. The voltage must be high enough to accelerate one electron toward the positive terminal of the junction. During this travel, the electron will bump into other free electrons, and now we bump into others and bump into others. We call this as an avalanche effect when that occurs. When that happens, we're going to start pushing current reverse through a reverse bias diode. So that thing's going to be dropping maybe 40, 50 volts, right? You understand? Once it breaks over, now you got I times R, or I square R, excuse me. These guys are going to bop real fast. If you break them over and you don't protect them, they are going to be, and normally we don't protect the reverse bias. The rapid multiplication of the conduction band electrons was called an avalanche effect. The reverse bias that causes the avalanche is referred to as the reverse breakover voltage, usually labeled VR in data sheets. So all your semiconductors are going to have a reverse bias breakover voltage. If you exceed the breakover voltage for the solid state device, there is a high probability that something's going to happen. Either it's going to short or it's going to open. Normally resistors, I've never seen a shorted resistor. I've never seen a resistor short. I've seen a shorted resistor, but it was, somebody did something wrong. They was soldering and dropped a solder blob across the things. Or when they clipped the leads, they clipped them too long, and when they press it up against something, the leads touched. Resistors, when you heat them up and they start going bad, their resistance goes up. Solid state devices, they can become leaky, which means they conduct when they're not supposed to conduct. They can open, or they can short. And they can pop on you too, by the way, if you screw up. So this is why we make sure we wear safety glasses around these things. If you do something wrong, it's going to pop. And usually they're made out of plastic. We do have some made out of metal, which are not as dangerous. But some of your cheaper ones and little ones are plastic. And when they pop, a little piece of the plastic comes flying off and it gets in your eye. We don't want you to talk about that. So we call it the risk. So we have three ratings. We have VF. What's VF? That's going to be the forward voltage drop the diode has when it's forward biased. We have what we call the reverse breakover voltage, VR. This is the voltage. If you exceed it, you're probably going to damage the diode, right? And then we have VR. This is VR. And then we have I. Usually they give you the maximum current. And then they give you the average current. It's what we rate at. So a single PN junction, we refer to this as a what? Diode. And I think the symbol's next. So in electronics, instead of drawing junctions and trying to draw pictures of devices, we come up with symbols that we represent in a schematic, right? And this is supposed to be covered in, but most people don't because it takes so long. Then we put a bar right here. This is called the cathode. This lead is the anode. And this is the symbol for a diode. And I explained to the class the other night, when the diode symbol was originally developed for vacuum tubes, they thought that current flowed from positive to negative. And we still call that conventional current flow. But actually what they're teaching is whole flow, right? You understand? We teach electron flow, so what happens is when it's forward bias, current is flowing against the arrow. Rectifier small, so we have two categories basically. We have rectifier diodes. Rectifier is anybody know what a rectifier is? Yeah, these are diodes that we're going to use to convert AC to DC. And then we have what we call small signal diodes. We use these for isolation. Normally we use them for logic. So the original logic that we used, and they're still used, we call it diode logic. So if you're familiar with logic, we have ands, nands, and that kind of stuff. This is what these guys are reserved for. We can use them as rectifiers, but what you're going to find out is their breakover voltage is usually a lot lower, and their maximum current is going to be a lot lower. But some people, it depends on your power supply, right? Does that make sense? And it will usually be given on your data sheet what category each one of these two categories will work with. So a standard diode, a signal diode, and a small signal diode and a rectifier diode, these guys are not designed to conduct in the reverse breakover region. If you break them over, they're going to be what? Damaged. We have one diode that we're going to have a very long lecture on. This guy is called a Zener diode. And we've changed the symbol a little bit. And so this is the symbol of a Zener diode. And these are going to be our voltage regulators. Y'all know what a regulator does in electronics? What would y'all think it does? So your cruise control is a regulator. What does it do? Even though you're going uphill or downhill, it tries to maintain a certain speed. Well, a voltage regulator, there's no such thing as a source that has zero resistance. Y'all understand that? So that alternator out on your car, you can take it apart and you can get an ohm meter and you can measure across it and you're going to measure ohms. But it's regulated. So what happens is that it's got a sense circuit out there in the regulator, and what it does is when you try to load your alternator, and as soon as that voltage tries to drop down because of the internal resistance of the alternator, it raises the energy to the rotator, which keeps the voltage up, right? And if it tries to go up, it does what? It changes the energy and make it come back down. So regulated voltage sources appear to have zero internal resistance, and those things are dangerous. They'll burn stuff up as long as you don't exceed the limits of the regulators. So Zener is the main device we use to have regulated power supplies. So what that regulated power supply does is if I come over here and put a load on a battery, so if you got a battery, it's not regulated. You can measure that sucker with a voltmeter, and you can take a resistor and put across it with your voltmeter. As soon as you connect that resistor, the voltage is going to drop. What causes it to drop? The internal resistance of the battery, right? You understand. Now, the bigger the battery, the less internal resistance it has, so the more current you can get out of it. But you could take a D cell and put your meter across it. You hook a resistor up to it. As soon as you hook it up, the voltage is going to do what? It's going to drop because of the internal resistance of the source. Car batteries have almost none, right? So you got to be real careful on a car battery. But they all have source. They all have it. So go out there to your car and put your voltmeter on that thing, put it on the battery, don't crank your car, and turn the lights on. As soon as you turn the lights on, what's the output of the battery going to do? It's going to drop down some because of the internal resistance of the watt. Crank your car and look at the output of your alternator and turn your lights on. Odds are it's not going to change hardly anything because that is what? That's regulated. We'll get into regulation a little bit. Zener is the main diode that sets the reference for regulators. And we put this sucker in reverse bias. But we always protect it with a resistor. We always got to have a resistor because if we break it over and we don't have that resistor, it's just on a regular diode, we would have to protect it with that 10 gig ohm resistor. Over here, we're going to protect this thing with ohms because it's designed to be broke over. And this book talks about it just a little bit, but we don't get into power supplies until later. So we're going to start off with what we call unregulated power supplies. So an unregulated power supply, what do you think will happen? Well, when I load it, the output voltage is going to do what? It's going to go down. When I unload it, it's going to do what? Go up. We're going to look at filtered power supplies. Then we're going to move over to regulated power supplies. And regulator, we're going to add regulation to it. So that means when we load it, as long as we don't exceed the limits of the regulator, the output will stay almost constant. There's no such thing as a perfect regulator. It's just like there's no such thing as a perfect speed control on your car, right? So what we can do is the diode, we need to be able to identify the what? We need to be able to identify the cathode and the anode. And what determines the size of the diode depends on how much current we're going to put through it. So we got extremely small diodes. I don't see any D's on here. I saw some inside the meter. We passed one around the other day. What did I do with it, really? So on your diodes that you can actually hold in your hand, on the small one, what they do guys are just on these are the diodes we're going to use. They're called 4000s, 1N4100s. You know, they have basically the same forward characteristics, and what varies between the numbers is their breakover voltage. So the higher the number on the 4000 series, you got a 4001, 4002. Well, the 2 would have a higher breakover voltage than a 1. So this is a pretty standard diode, and I need to go in there and get my diodes out. So my miscellaneous diodes as soon as my camera comes up. Come on, come on. We'll try to get it to focus in on this. So what they do is, can y'all see the band? So the band end identifies this lead as the cathode, and this lead right here will be the anode. And this is pretty standard. Huh?
It's just some production.
Yeah, right. So bar on the side. Let me pause this. Y'all remind me. By the way, I think I told y'all this. I have a tendency to pause the lecture. So what we got to do is we're going to go ahead and take a break. What we'll look at is we're going to have to get because the only requirements for this class is DC. But we have to, if we're going to understand how we convert AC into DC, then we're going to have a little bit of knowledge about what? AC. So the next, what we'll do next is we'll look at AC. We're not getting into there's a lot more to AC than what we're going to teach. So we're going to teach AC from just taking AC and converting it to what? DC. But we'll have to learn peak and cycles and frequency and a lot of different kinds of stuff we'll have to get out of the way. All right, so y'all guys go ahead and take a break while I switch over here. And I don't know where my other PowerPoint's been.